Well, hello again. In this example, we are going to practice the generation of shear and moment diagrams for beams. We'll take a look at this fairly simple looking beam. Note a couple of things going on in it. We've got an applied moment there at midspan, which then produces the reactions of M over L. Notice the overall length of the beam is L. We will start looking at this by identifying the load discontinuities, which we had that one at point B. Wherever the load discontinuities are, we'll draw a vertical dashed line, just so that we don't forget that in the process of our computation. And then we will go ahead and label our diagrams, our axes here. Here's the shear diagram, here's the moment diagram. Now I'm not going to provide units on these because we are doing this symbolically in terms of M and L. The next thing we're going to do is we're going to plot the value of shear at each end of the beam. Remembering sign convention, if we've got a force here at the left end, if it's causing a counterclockwise rotation of the member, that is a negative shear. And so we know we've got that here, negative M over L. Now at the right end of the beam, once again I want you to take a look at that direction. It causes a counterclockwise rotation, so that is a negative shear, negative M over L. What we want to do is we want to then go back to the far left end of the beam and, following our rules, go ahead and identify the values at intermediate points. So the change in shear from one location to another is the area under the load diagram. So you'll notice right here on that beam there is no load, so that means there is no change in shear from point A to point B. So we get this negative M over L. We use the same rule, noting that there is no load here, so the change in shear from point B to point C is 0, thus producing the same moment. We do wind up at that same value that we had already predetermined, so we feel confident in our mathematics on this. Because there is no load, then the shear will be constant across all of that. Don't be disturbed by that applied moment, because the applied moment only affects the moment diagram. There is no jump that occurs in a shear diagram due to an applied moment. But it is a discontinuity, and so when we go to generate the moment diagram, we do need to consider the moment at each end. So let's go ahead and do that. Since we see no moment arrow down here, that means the moment is 0 here. No moment arrow here, so the moment is 0 there. Now let's go back to the far left. So from point A to B, the change in moment from one location to another is the area under the shear diagram. So we're going to look at the area right here. And if you do that, the area will be computed out to be negative M over 2. And while we're here, let's go ahead and get that next area, because we're going to need that. Area is equal to negative M over 2. So we're back now down to our moment diagram. So the change in moment from point A to point B is negative M over 2. Brings me down here. Since shear was constant up above, that will make moment to be a first order line. Let's go ahead and shade that in. Now, what we do have is we have an applied moment at point B, which causes a jump. A clockwise moment causes a positive jump. So since it's an applied moment of M, it will jump a total of M, which will then bring my next point up here to be M over 2. Then change in moment from point B to point C changes by a negative M over 2, that's the area under the shear diagram, which will bring me back down to 0. That makes me confident in the computations that I have done. That is a linear line, what we call a first order curve, because our shear diagram was constant, which I refer to as a 0th order curve. That concludes this example. Remember, it's always a beautiful day to study structures.